This lab is about pressure. Pressure, as we learned in class, is the force per unit area. So on a surface, you apply a force and pressing on it. And the stronger the force, the stronger the pressure. But the same force, the smaller area, then you have a strong pressure. Therefore, pressure is force per unit volume. In fact, newtons per meter, okay, per square meter, per meter squared, Newton per meter squared. So that unit is called a Pascal. Once again, Pascal is a pressure unit. It's got newtons of force per square meter. Think about a meter with a square and how strong that is. But this lab actually study the pressure under liquid water. Starting from the link over here, and you will see this website, and you click here, and the first one, then just wait a couple of seconds. All right, so we have this like water tub, and we can just fill water with it. And then down here you have the drain. Just play with it. So you can let the water go, or you can close, let it go, all the water is go. But you can again add more water. So and then you have a ruler over here, and to see how high we can go, almost up to say 4 meters, and actually 3 meters at most, 3 and a little more meter of water. And then, so that's the system, okay, we're going to play with. And here, you can play with other things too, water tower and flow. If we're going to study this later on, but today we just use this one. And now, so what do we do? So pressure is the force, and then air is gas, will have pressure on any surface, and then you have a pressure gauge. So there's air around us all the time, so then you will have pressure. So there's a pressure gauge, you see there's a pressure gauge in the air, and then that's called a 101.311 kilopascal. Okay, so Pascal is a small units. So 1 Newton is a force, and in 1 square meter, that's a very tiny pressure. But actually the air exerts pressure on everything, and that is a very strong pressure. Okay, and that's about 101 kilopascal, which means 1 square meters, you will have about 100,000 newtons, right? So 1 square meter, you have a 101,000 newtons, so very strong pressure, because that's why there's a one pressure. Imagine all this whole column of air stack up to 20 meters, and we are at the bottom, therefore we have this much pressure. You see, but if you go up a little bit, so the pressure changes, but it changes very slowly. See, it changes in its digit. So you go up and change a little bit, so 303. So now you go up 301, but if you go 20 miles above, and then it will change to 0, because that's outer space, you would say. So the pressure is about 101.3. We call that standard pressure, right? So basically it's this number, and depending on temperature and humidity, and this slightly change, but since we are jumping just a few meters over here, and it's basically, we can say the standard atmospheric pressure at the sea level is about 101.3 kilopascals. Something like standard pressure on the ground. That's all due to the air on top of us. So as we go up, see the pressure go low, low, low. See, this number goes down. But if you go to 20 miles above, this will reduce to 0. But around here, it changes slightly. Change only 1,000, so we don't care. But so if you change like 20 meters, yeah, still 101, so not much. So now But now that's the pressure on the gauge, on the wall, because of the air condition. But now, if you put the pressure gauge in the water, so the water has much higher density. Water has much higher density, and then all this weight of the water is on this thing. Because of fluid of the nature, the pressure goes all directions. That's isotropic. Once you go to the water, so that's the air, right? So it changes slightly. But once you get into the water has a very strong density than air. It will change much faster. See, it's changing in one digit. Every time you go back, it's 1,000 pascals. See, once you go into water, it goes very fast. Every time you go down by, so because water is heavy, so it still go up. So that's this lab is about. So now if you go over here, and that's about 101, that's because of the air. But say you come over here to remove the air, atmosphere off. So see, watch the gauge. Boom, and it becomes 0, right? Because there's no air. But now of course 0, 0. Once you get into this water, and then you start having pressure. Of course, that's all pressure is because of the weight on top of the gauge. And you go to the bottom and deeper. That's how you dive deeper and dive deeper. So that's the pressure under the liquid. Now, so that's without air. Then once you add on the air, boom, see, 109. So that's normal case. Of course, we're not able to remove air, but that's just the concept. So it's good to have a simulation like this, so you can say, well, if water would go, or if the air would go away, what would be? So the underwater, so the pressure under liquid is actually two parts. One part is the liquid itself, the weight. Another part is the air, okay, on top of it. In fact, the dominant part most of the times is the, like in the swimming pool, is air, but then of course it goes down much deeper. So if you turn off the air, watch this gauge. Over here, turn off the air, boom. So that's much less, right? 18. And you turn on the air on top, boom. It's about 100 more. So that's because that's the situation. So, and it changes fast because of the weight, and then change slow. So that's the goal for this lab. Now, okay, the pressure inside the liquid is isotropic, meaning it has the same value in all directions. Pressure in a liquid comes largely from two sources, as I said, gravity in the atmosphere. And then the first is simply due to the liquid's weight, right? That's what the liquid weight. And the second is due to the collision of molecules normally on the air of the surface, okay? Which is also have the origin of the gravity. So there are two parts. Static pressure, liquid is the function of depth. So we talk about constantly what is a function, or one quantity depends on another. So function is the pressure, it depends on the depth. When the deeper you go, the higher the pressure. This is a nice picture. So inside the water, there are two parts. One is from the air on the top. So that's 1 atmosphere pressure is about 101 kilopascal. And once you go in there, there will be more because that's this, but also add this water on top. The deeper, and go very deep, so then you see the pressure doubles. If you go as deep as like 10.3 meters, and then actually it doubles the pressure on the surface. That's called atmosphere pressure. So therefore we have precisely two formulas. One is an imaginary formula. Without air, we remove the pressure on the top, okay, and then there will be density of the water or the liquid, and the gravity, and then the height in meters. So density is in kilograms per cubic meters, and for water is 1,000 kilograms. It's 1 ton per cubic meter. Cubic meter is huge, right? 1,000 kilograms cubic, and then 9.8 meter per second squared, and that's in meters. Yeah, you can simply use this quantity to calculate how many kilopascals the pressure is once you go to the water. That's important. That's without air. Okay, and then normally, however, everything is around is immersed in atmosphere. So then that term is due to liquid, and then on top of it, it is this air on top of it. So that's 101.32. So then we're going to explore this concept. So what do we actually do? So we fill the top with water and we empty this and close the drain. So first we empty this and close the drain and click on atmosphere pressure, okay, and start to fill in the water and measure the read corresponding pressure at the bottom of the gauge. Enter the measure of the experimental value in the top tab. So then this is very straightforward, and let's see. I just quickly do this. First, what do? And you let go of water. All right, so then you put this gauge at the bottom. All right, so let's see what I want to do. First, turn on the atmosphere pressure. So we're gonna do one with pressure, without pressure. So then you will have this with atmospheric pressure. So this is at the bottom of water, but there's no water. And close this. All right, and then you're gonna turn on the water. So let's see, no water. Okay, no water, but it's 101.36. All right, so then let's see. You enter this into no water, 101. Okay, you just put in this part. Okay, and then also you do theory. Okay, the theoretical calculation you will do. So you enter over here, and then so that's no water. So then you start adding water. So with no water, it has this much pressure purely due to the air. Now we start. The second point is adding 1 meter depth of water. So let it immersed in the water for 1 meter. How do I know it's 1 meter? I have a ruler down here. So I will go from here to 2. So then now you start feeling this. As the water goes up, you see the pressure goes up, right? Very quickly, because water is heavy. So, and that is simply due to, you can say based on your intuition, because of the weight of the water. So, and then that's on top of the atmosphere pressure. So how much did it go up? And then just write down with air pressure on top, and then at the bottom, 1 meter below water, it is 107. So then you will have entered this 107 over here. So 0, 107. So this, no, I did over here. You enter to this experimental data 107, for example. All right. So if you put here 107, in this case, I just did. I'm not going to finish all this, but I just show you what you're supposed to do. So that is (107), for example. So 0 is at 101 point something, because that's the air to start with. Every time is a little bit different because of different weather, different pressure. You hear the meteorologists say, well, atmosphere pressure was so and so, but it's all around 101 something. The difference is only in the last few digits. But then you go 1 meter down, it will be having like about 10 kilopascal higher. And then, so then of course you add 2 meter of this. Now you get 2 meters, so you get, watch this number, you get 2 meters. All right, so 120, you put this 120 in that experimental column, and then you put 2 and 3. That's all we can do. So 3. So that's the with air. Now if you up this table, so with air pressure, that's sort of realistic. At the same time, you can do the calculation, theoretical calculation with this formula, like this. So this formula, so we like this with air with this formula, and so you have 1000 and G and 1000 per cubic meter, 1000 kilogram per cubic meter, and 9.8 meter per second square, and whatever 1, 2, 3, 4. Let me demonstrate my rough calculation on this. All right, you also need to do this theoretical calculation, use this formula, and this could well be a exam questions or homework question. So the pressure as a function of depth. So rho is density, G is gravity, and then H is how deep it is, and ATM and atmosphere pressure, and normally it's this number 101.4, 101.3 kilopascal. So let me see. So that's actually theory. So these are the data, and this is simply a copy of from my notebook. So for example, 1 meter down. So if we, what's the theory? So theory goes without air. All right, without air is just rho G. Without air, so 1000 rho, and atmosphere pressure. Actually, that's the gravity force, and 1 meter. So that multiplied easily. And then you have 9.8 kilopascal. That K means 10 to the third. So kilo. So that's the kilopascal. And 2 meters down, then of course the rest is the same. Then you have a 2 here. Well, my 2 is not quite a 2, but 2. And then you have 19 kilopascal. That kilo comes from this 1000 kilogram per cubic meters. And 3, and that's 29. Then 4, you have 39. So it goes linearly up, and that's no doubt, because everything is the same. This depth is just 1, 2, 3, 4. So it's a linear function. This is without air, because just the liquid. Then with air, then you will have the other formula. With air, as this first term is the same, you simply add this atmosphere pressure. I just use 101.32 kilopascal. Down here with air, 9.8 kilopascal, so 9.8, that's without air, that's term, and plus this term, that's the standard pressure, because the only difference is the last digit, 101.32, and this time we just use this number. So then this 9.8 plus this is 111. So that's 1 meter down. So, and this, see if you read the meter reads, that's a theory. And then this 2 meter down is 19, and of course the same thing, adding 120, and then you simply across the board adding this number. So, and then that's it. If you want to plot this differences, like, and if you would imagine the situation, of course that will not in reality happen, but without the air, you simply go from 0 to about 40. Okay, so 0, 9.8, 19.6, and so that's the pressure of the liquid if you go down. Okay, 1 meter, 2 meter, 3 meter, 4 meter. That's the theory. And then with the air on top of it, and then simply adding this much, 101.34 up. So you plot like this. So now we do without air, so it will be theoretically basically this first term in the formula without atmosphere pressure, and it will be this, so 0 and 9.8, 19. So that's it was a imaginary situation. So when you go to, there's no air on the top. So without air, we do this experiment, we let all water run out, and then, so that's the pressure. There's still just air, so we go here, we just return one of these, and then without air we turn off the air. So watch, that's obviously a imaginary situation, so boom, air is off, and so this all turned dark, and that means something. Okay, if without air around the earth, actually your sky really go dark, of course with decorated with some stars and there, but basically dark, because it looks bright because the air scatter light, even light go this way, and then the air molecules get scattered all directions to make the light. scatter actually blue light, so make the sky looks blue. But without air, the sky actually looks dark, okay, totally, but with some stars in the middle. So that is the side point we will, when we learn optics, electricity, and we will learn that. But here, without air, look, the pressure is 0. So any gas, the pressure is due to molecule collision, bending on the walls, and but then there's no pressure, so there's no pressure, right? 0 and 0 everywhere. So with no air. Now you close this, so now you start adding water. So you see, well, and let's adding 1 meter. One meter. Not quite yet. See, 1 meter exactly. In fact, there's 9.8. You may wonder, does that has to do 9.8 the acceleration? Yes, it does, mathematically, and that's the beauty of SI units. I will ask you to prove this number numerically, even though it's pressure. 9.8 is coming from the G, and then because 1 density and 1 meters, and then therefore G, that numerical number becomes the pressure units, so 9.8. So therefore, you increase 1 meter of water underneath, you have 9.8 kilopascal. So then of course you put into that table, okay? Put it into that table. And you put into table 9.8 and 19.6 and 20.9. So that's the theory calculation we already have. Experimental, you're going to see what's going to have. Of course, obviously it's going to be the same, but I just want to be to show you how it is. So now 2 meters, so it's doubles, and because that's the weight. So it's 19.6 and 3 meters, and see how accurate you can do. So it's tripled. We can just do like this. Okay, you're going to fill up this by doing experiment, and you're going to do calculation on paper. See if theory and your experiment matches. And then number 4, you're going to make it once you have the data, actually just record we did 2. One is with air and one is without air, which is the second one is the imaginary situation. So we're going to plot the both experimental case with air and without on the same graph using Excel. Okay, and so this is, let's see how you do with Excel. In fact, let's see how you do with Excel. Actually, you already know how to do it, and I have actually a sample data, but I hope you start your own. But I just show you how you enter depths of water, and then 1 pressure, that's the real pressure, and that's without air. So of course, so this number, and this is with air on top. Basically, you can see is add 101.3, or see if it's 0, it's nothing, and here you have, because of the air on the top, and 101.3, and then 9.8, you add 9.8, you get this. So you have this. So then let's just plot, and that's simple technique. And of course, insert, plot. This one is my favorite. So that's it. Okay, that's the chart. And then you will put, I want you to change this, say static pressure, okay, under water. Okay, and so then of course the units will be kilopascal. Pascal is Newton per meter squared. And then of course this one is without, the bottom one is without the air. So that's simply the water, the weight. And the actual pressure is this, because the air is on the top, and you have this thing. And then this is what you do in the lab. After you made your plot, you want to insert this into here, and then this part 5 is basically kind of like a question. In fact, the atmosphere air also changes with height. Actually, the same idea, kind of like a liquid, because of the weight of the air. It's very light, but doesn't mean no weight. Because if you have 20 miles of air column pile up, and we are actually underneath that 20 miles of air depth, so that's quite sizable. That's give rise to the atmospheric pressure. But if we just, because it's 20 miles, if you go 1 miles or 1 meters or a few feet up and down, and it doesn't change much. It does change, but so then I just want to compare how does it change with the height, the pressure in the air and in the water. Obviously, in the water it changes much faster, and you can get online and see what is atmosphere pressure with height. In fact, that is how airplanes detect how the latitude, the altitude of the aircraft. So they have a pressure. Okay, when you go higher, the pressure is lower. So basically with the pressure, they know how high the airplane is flying. So that's a very important idea. But it goes slowly. But slowly compare with in the liquid. So now then we have all these questions. First question to you is, the static pressure increase adding 1 meter in depth of water. What is the static pressure increase adding 1 meter of water? So it's like adding 9.8 kilopascals per 9.8 kilopascals per meter. So that's, and then of course, you will learn in class, this will require you to do some homework. How much in units of psi? That's tire pressure. How do we convert that 1 meter of water, and how much atmosphere? And there's called a bar. Those of you who study biology or medicine, and the mercury height. This is all pressure units. So 1 meter depth of water, you go down, it will increase. Well, if you use the standard units, it increase 9.8 kilopascals. And how many psi? How many atmosphere pressure, bars, and mercury height, and you all need to find out. So I will ask you these questions. What is standard atmosphere pressure in kilopascals, psi, and mercury height? So once again, the standard atmosphere pressure is just the pressure, what do you feel now? Just on the Earth. So, but that's standard, because it's up and down, it's like standard pressure at 0 degree temperature and standard pressure, and near the sea level, and that's the standard pressure. It has a value around 101.2 or 101.34, and then of course normally because the weather changes go, but that little bit human can feel, which is always 101 point something. Okay, so that's your homework. Okay, and also you will compare the standard atmospheric pressure caused by the depth of water. How many meters? Okay, if you go down, the temperature goes up. Oh no, the pressure goes up. And if you go deep, and pressure goes up. And of course, you go to so deep that actually it's doubled the air pressure, because air pressure is on the top, so it's like 101. And this question asks you how low you go down, and so the pressure actually twice as much as the air pressure on the top. All right, so then of course that's all due to the gravity of the weight, okay, on top of whatever the object immersed in the water. Okay, and then number 4, and acceleration due to gravity is this. So this is a related question. Okay, that's all because of this gravity attractive force. Its value varies slightly from different place to place. Okay, and what would you say the most commonly accepted value? So standard gravity. So this 9.8 is what we use for the school for calculation, but which is correct. But in fact, because that's due to the universal law of gravity. Because on the Earth is not uniform, and there are some places the higher, and some places the lower, and some places have even magnetic field, and then this gravitational acceleration actually changes a little bit. For example, in Colorado, this will be less, okay? And different places, some places 9.81, some places 9.80, and some places 9.79, and so on. So, but of course, school 9.8, but that little difference different at different locations. So find out what is the standard accepted value. Give 3 digits. All right. If you have questions, you can always send me an email, and we can discuss over the Zoom and so on. So have fun with the lab. So that's it.